So now it's time for us to discuss alkynes. So alkynes end in YNE, just the same way that alkanes ended in ANE, and then alkenes ended in ENE. So now what we say is alkynes are YNE. Keep in mind that when we're dealing with sp carbon or alkynes, we're dealing with sp carbons. Remember, alkanes were sp3 carbons, so the bond angle was about 109.5. Alkenes have sp2 carbons, so there's a bond angle of about 120. But sp carbons have a bond angle of about 180. And what this translates to is the fact that we have 4 carbons here in a row that are probably lined up there. And you may not notice that there's a triple bond between 2 and 3, but absolutely there is. And so what that means is that there are 4 carbons there in a row. Alkynes are linear. Keep in mind there's 2 unhybridized p orbitals that kind of run in a plus sign to each other, which almost makes like a tube of p electrons that are unhybridized that are being shared between those 2 carbons. So there's a lot of electrons going on in that process. So that's going to be our 4 carbons in a row, and C2 and 3 are sp hybridized. So that's linear. If you've got a terminal alkyne, it'll just stop at the triple bond. Okay. Alkynes, because of the fact that they're linear, cannot usually be in rings. You'd have to have a really big ring that is kind of straining on other carbons because of the bond angles. But you'd have to have a really big ring to be able to put a straight line in the middle of it. So imagine that as you're trying to put together your molecules, that if you had maybe 10 carbons, there's going to be a lot of strain in those carbons when you start trying to pull and push around a line in the middle of a ring. When we go to name alkynes, we need to replace the parent chain, the ending of the parent chain, from an ane to an ine. So when we change the end of the word, you definitely want to use that functional group in your naming of that particular thing, whatever that is. So, for example, what we could do though is when we're naming this first guy, you want to include, you want to include the triple bond, right? Now, counting this again is something that you have to be really careful with. So 1, 2, 3, 4, 5. When you name something and you change the end of the word, that becomes the top priority. So that becomes 1, 2, 3. Now there's 3 ways to actually name this. We can name it as 3-methylpentine because it's assumed to be on the first carbon if it's not stated otherwise. We can name this 3-methyl-1-pentine because you're putting in the 1, even though that's kind of unnecessary. Or we can do sort of what the new version of that is, and that is to name it with 3-mental-pent-1-ine. And so yes, this literally puts a number in the middle of the word. Some people like that, some people don't. It also kind of depends on what it is that you are trying to write and name that might make a difference to you. Okay, in this next one, we've got a triple bond right here, and we have to decide which way to number. If we number this way, 1, 2, 3, 4, 5, then the number for that will be 3. If instead we number 1, 2, 3, 4, 5, then the number for that triple bond will be 2. So that takes priority. So this becomes 4-chloro-2-pentine or 4-chloro-pent-2-ine. There should be a dash there as well. Now, if we can name either direction in order to get to the lowest number for that triple bond, you definitely want to do that in a way where the substituent will get the lowest possible number. Because it's going to be the case that you're going to end up with a 3 if you count from right to left, or if we count from left to right. So definitely want to go this direction because it also gives that bromo the lowest possible number. Okay. Okay. Due to the fact that we have a greater S character in the carbons that have a triple bond in them, this hydrogen, if you've got a terminal alkyne, is more acidic. Its pKa is about 25. So it's not incredibly acidic, but it is a little bit acidic, which means that if you add a really strong base, like the one we use most often is NaNH2, then what ends up happening is that NaNH2 will grab that hydrogen on the end, and you'll end up making a negative charge right there. So now the cool thing about that is that we can use this as a true carbanion to combine with other things and extend carbon chains. This is a really, really powerful reaction. So we're going to use this when it comes to synthesis. Next, we need to know how it is that we make alkynes. There's two ways to do that. You can either have leaving groups here and here on 2 carbons next to each other, which will then allow you to make this triple bond right here. Remember that this is large amounts of base, so we would have excess amounts of base, at least 2 equivalents, or in excess. So you can do this with like KOH, you can do this with NaNH2, that's fine. It just depends on what it is that you're trying to do here. In the same way, we could end up using both of these if they're on the same carbon in order to make a triple bond as well. So here again, we can use NaOH in excess, or we can use at least 2 equivalents of base. So it's going to take a minimum of 2 equivalents. Usually takes a bit more than that to actually get the reaction to go pretty well. If you have a longer chain with a strong base, the elimination direction is determined by small versus the large base, just like we did with Hofmann elimination versus Zaitsev elimination. So that's what's going to make a bigger difference there. Okay, now we go into several different types of reactions. The first we deal with is hydrogenation. So if you remember, when it came to double bonds, we could add H2 with either platinum or palladium. And what that does is effectively get rid of that double bond. So that's what you see there in that first reaction. Well, if you do the same reaction with a triple bond, you get the same product. So that totally works. But what happens when you want to stop at the double bond? Well, now we've got 2 things to consider. We can either end up getting a cis alkene or we can get a trans alkene, depending on what our reagents are. Lindlar's catalyst is basically a poisoned or a deactivated form of the same thing that we were already using with platinum or palladium. Okay, it's when combined with H2, will take a triple bond and stop it at the cis alkene location. On the other hand, if you use Na in combination with NH3, and please know that this is actual sodium, not Na+, this is Na with all of its electrons, which means that it's desperate to get rid of one, followed by also you're putting in there with ammonia, so NH3. What you end up getting is this transalkene. So this is not NaNH2 where you have a really strong base. So Na plus and NH2 minus is what we were using before as a base. Don't let that confuse you with Na solid sodium in ammonia. Okay, so just emphasizing that. That gives us the trans-alkene. So let's go through the mechanism for how this one works. Now, we haven't seen this before. What we're going to look at with these mechanisms is the fact that you've got one electron that's moving at a time. And so we're just going to use this type of arrow. What that means is if you just have a hook, that means you only have one electron moving at once. So this becomes a lot to follow, especially when you have radicals involved. So keep in mind when it comes to sodium, remember that sodium has one valence electron. Metallic sodium is desperate to get rid of that extra electron. Remember why is because it's trying to be like noble gas configuration, which it has underneath that one extra electron. So it pushes that over to the carbon here that's involved in the triple bond. And yes, that means a radical is formed. But before the radical is formed, we have a negative charge right here. Before we worry about that radical, I should say, we have a negative charge right here that is more reactive in the presence of ammonia. It goes and it grabs that extra hydrogen and makes that negative charge kind of go away first. Then another sodium is going to donate its electron to where that radical is right now, giving a negatively charged carbanion that will react with yet another hydrogen. And in the process, what you end up with is a trans-alkene. Why does this happen? Well, because you're going through stepwise progression here. Remember that a trans-alkene is more stable than a cis-alkene. So it's actually harder to get the cis-alkene in the fact that it wouldn't happen if you didn't add two hydrogens at the exact same time. So we end up getting a trans-alkene here. But remember, when we're dealing with this catalyst, these Lindlar's catalysts are flat. So they have hydrogen sort of on their surface. So when this comes as a triple bond, like you end up having those hydrogen that are transferred kind of all in one. Okay, so they're coming off the same direction. And that's the reason why we end up with a trans-alkene with sodium and NH3, so Na and NH3. Versus we end up with a cis-alkene when we're dealing with Lindlar's catalyst. Okay, next let's talk about hydrohalogenation. Remember, with a double bond and hydrohalogenation, what we ended up with was a Markovnikov product where your X is going to go to the most substituted carbon. Well, that's kind of what happens when it comes to a triple bond as well. And if you continue to add excess HX, you will get two of these in there. So keep in mind one thing. So when I'm showing you this twice, another way to draw that would be if you had this and you added HX, and sometimes we put just XS to mean excess, and that would be what you would end up with as an X. Oops, sorry about that. And another X right there. So this would be another way to write that you have at least two equivalents or more. You could say two equivalents instead of excess, that's fine. Sometimes we want to put in a little bit more than that just to make sure that we've got enough. But here's the thing. Even though we went through a carbocation intermediate when it came to CC double bonds, which is what I've got written down here, right? You end up with a carbocation intermediate, and then that X minus is attracted to that carbocation. It's a slightly different mechanism when it comes to a triple bond, or this is what experimental data sort of shows. Here, what it's actually showing is that we have sort of two HX molecules that are involved in this process simultaneously. Why? Because the transition state on a double bonded positive charge doesn't really exist. So you can't, that's just too high of energy to make that, which I've showed you all before, in that you can't really make a vanillic carbocation. Well, so as we have this stabilized structure here, it's kind of just doing two things at once. Now, here's the thing. The effect is kind of the same thing. So you end up with X there on the Markovnikov side, and the X and the new H that was added are going to be trans from one another. I don't really need for you to know the mechanism of the triple bond. I do want you to know that of the double bond, but I wanted to show you where that came from, okay? Now, it is also true that if you were to use a triple bond with HBr and peroxides, then we do get an anti-Markovnikov bromine, both in this format and in the cis form. And again, if you started to add extra, you'd end up with two bromines there. Okay. Next and last for this video at least, we're going to talk about hydration of alkynes. And this is also very similar to what we saw with double bonds. Remember, when you have H2SO4 and a double bond, we end up making the Markovnikov product. Remember that you can also use HGOAC, and that's a little bit more stabilized version of H2SO4. You don't end up getting a carbocation that can move around all the time, and it just makes it a little bit easier to deal with. Okay, so that's going to give you the Markovnikov product. On the opposite side, if we used BH3 and THF followed by hydrogen peroxide, water, and NaOH, we got the anti-Markovnikov product. Remember, that's because BH3 is going to go to the least substituted, or the borane is going to go to the least substituted carbon that's then going to be later replaced with OH. So alkynes are going to follow that as well. The difference is they produce enols. And what is an enol, you might say? Well, an enol is when you have a double bond or an ene that's then connected to another functional group of an alcohol. So there's an ene bond and then an alcohol. And I always joke that I think it sounds like a donkey because it's an enol. Anyway, well, just like what you would think if you had a donkey in there, they end up kicking something out. So let's look at that. When we deal with triple bonds, it's just kind of like we did when it came to your double bonds. You can't deal with the positive charges. We can't deal with a vanillic carbocation, just like I was saying in the last slide. So we can't have that. It's just not going to happen. So here we almost need to use HgSO4, water, and H2SO4. So we kind of combine what we had with the double bonds. And what we're going to do is we're going to make an enol intermediate. So see how that double bond goes where this was, and we end up with an OH on the Markovnikov. Markovnikov side, right? Since we have acid around, there is what's known as an acid catalyzed tautomerization. And so you end up with the ketone. So let's look at that mechanism. Let's look at the mechanism just for the acid catalyzed tautomerization. Tautomerization just basically means you move things around to give different functional groups, or it changes its perspective, if you want to think of it that way. So if we have a enol, keep in mind we've got acid around, so if we've got acid and water, what that really is H3O+. The double bond will come over and grab that hydrogen, electrons go back to the water, so the water leaves. And then this kind of like change takes place, and it's sort of going back and forth. After you take the electrons from that double bond over to the hydrogen, that's going to leave a carbocation right here, which of course oxygen is attracted to that positive charge, so it donates in its electrons. When it donates in its electrons, the positive charge now resides on the oxygen. And so another water molecule is going to come out here, grab that hydrogen, and electrons go back to the oxygen. and that's where we end up with the ketone. And guys, this happens really quickly. So when we look at this reaction, what we really see is this product. So we don't even need to write the enol intermediate, just showing you where that stuff comes from, okay? Okay, here's the cool thing. You have an acid catalyzed tautomerization, but you also have a base catalyzed tautomerization. So let's look at this from a different perspective. If we have BH, in this case, we're going to do R2BH, I'll talk about that in a second, and THF, followed by the things that we had before, so H2O2, water, OH minus. It's also going to make an enol, but notice that the OH is on the least substituted side. And once a base catalyzed tautomerization takes place, we end up with the aldehyde product instead of the ketone. Okay, so here's the mechanism here. Here we have OH minus, grab that hydrogen, electrons go back to the oxygen. There's some rearrangement that occurs. So the electrons from the oxygen go to this bond, and then those electrons that were currently in that double bond move over. That basically gives us a negative charge here, or as a carbon ion that builds up on that carbon. It will grab a hydrogen really, really fast, and that regenerates the OH minus when those electrons go back. And that's how you end up with the oxygen on the least substituted side and with a double bond, okay? So when it comes to triple bonds, we don't use BH3 because BH3 could react more than once, and it could end up giving us some other products that we don't necessarily want. So we usually use a sort of complex R groups around the boron so that you only have one hydrogen. The easiest one to write on paper is called 9BBN. You can have a similar type of compound with that. I tend to write 9BBN on paper, but when it comes to actually doing that in the lab, I might try different types of things in order to get what you need. Again, this is not going to be something that you need to write out the intermediate for. You could just draw that goes directly there. But you do need to know that these mechanisms work in both acid and base, and you probably need to know what those mechanisms are as well. So you need to be able to write those out. Hope that helps. See you on the next one.